Yeah, so in tic-tac-toe, the way we manage to transform inputs to outputs is by, first off, we have to identify what our inputs are, which is the player's chosen row and column, such as, for example, if we wanted the middle spot, we would ask the player would input row 1, column 0, because remember, programs generally start from row 0 to row 1 to row 2, not from 1, 2, 3. So it starts from 0. So if they want the middle spot in tic-tac-toe game, they would have to pick row 1, column 1. Then after we gather that input, we create a way to store our board, a 2D array, which can essentially just think of as a 2-dimensional graph. And we find the X coordinate, or in other words, the column of 1, and then the Y coordinate, which would be the row, which is in this case is also 1. And after you find the X and Y coordinate, you would
英文我听得懂，但他这是已经是第10几节课了，我现在从这样听，我还是听不懂。
Oh, do you mean that we explain some things then?
浪费时间。
Hello, Jin Xiang, did you have a question? All right, no questions. Don't worry about it. Yeah, so essentially, after we take that user input, we use a 2D array to store this input, because in tic-tac-toe and many other programs, a lot of the times the user input may not be necessary immediately, but will be necessary later. In this case, we have to be able to store the current user's inputs and all the previous user's inputs in order to actually display the board and to check wins and stuff. Because if we take in a player's chosen run column and just straight up forget it, then there's no way to ever truly finish this program, because then you'd be stuck in a permanent state of not being able to know when the game ended. So in order to sidestep that, we use a storage space called a 2D array. And then we simply use that to store each person's chosen row and column. And then at the end of each term, we would then print out this board as one of our outputs in order to show the player. And as operations, as our logic, we would then simply go through each of the possible win states and simply check if they were winning by going through this stored space, this 2D array, and checking for horizontal, vertical, and diagonal wins. And finally, if there was a win or a tie, that would become our that would then become our output, and we'd output it. So let's move on to the main topic for today, which is Connect 4. So Connect 4 borrows many elements from tic-tac-toe. Some parts remain the same. For example, input and output are virtually, it's basically the same thing. You ask the player for, while in tic-tac-toe you ask for the row and column, in Connect 4 you only ask for the row, right? Since you can't choose the column. It always goes down to the lowest possible spot that isn't being blocked by another piece. But other parts, such as the scanner, would remain the same. Except you're just getting a one input this time. And the output remains the same thing as well. You would print out the entire board, like in tic-tac-toe, and then you would have to print out who wins and who wins, or if it's a tie. So generally speaking, the beginning parts look pretty similar. First off, you create a scanner, and this serves as your way of gathering input, of gathering information from the user. Next, we have a system output line. While sometimes we use system output lines like do output, a lot of times you also use it to inform the user what to do next. So in this case, it's not really output, but more instructions, so that the user doesn't get confused. You will probably want to use lots of printouts or other ways of showing out information users. So that way, when you test it, you don't get lost where you are. And when a user uses it, they also don't get lost. So yeah, this simply asks the user how many rounds they are. And then you can use scanner, again, the scanner, in which we named the scanner SC. And we can call the scanner's method next int, which will return a number that is whatever the user typed into the terminal. And we will store it in a container that stores one number called number of rounds. Then we simply create some extra buckets here. In this case, the number of rows of our board and number of columns. These buckets are simply here to store the number so that it's easier to remember instead of having to rewrite 6 and 7 by simply putting it up here. If you ever want to call it again, you could just change the number up here. Like for example, if you wanted to change the number of rows, instead of rewriting the board with a number, by using a container, you can simply just change the container's value, like the 10. And this way, everywhere you need to use a number of rows, such as here or anywhere in the rest of the program, you don't have to change it for each one. By using a bucket, since this bucket's value is shared across everything, you can just change the bucket's value. But in this case, you want to leave it at 6, since that's the general Connect 4 board. Yeah, and also I will put this code on Google Classroom later if you want to look at it again after the class. Yeah, so here we start with the main important parts of the program. Well, this is where we start actually doing the logic and the actual programming part. Because remember, most programs, the most meaty part is the operations where you transform the input into the output that you want. So in this case, at the beginning of each round, we tell the program to create a new storage space. And we call it board because it's going to represent the board. You could name it anything, but it's always a good idea to name it like after the thing it's supposed to do rather than some random name, because otherwise that could be confusing. Yeah. Then we create a Boolean variable. Remember, Boolean variables are similar to most other ones, except instead of storing a number or a word, they store true or false. They can only store 2 values, and it can only hold one of them at a time. So in this case, win is equal to false, and the only other variable it could possibly equal to is true. Booleans just simply mean a container that stores a true or false value. And we create another new bucket that represents the current player's turn, because we need to have some way to remember the turn. While we could just rewrite the code so that it just does each player side by side, by doing it this way, we can it makes the code easier to read. So in this case, I added a comment saying in this case, in this Connect 4 game, if their player bucket is ever 1, it means it represents the player who's using the red piece. If it's ever 2, it represents the player using the black piece. Right now it's representing player 1 or red. And here we have to start a while loop. The reason we're using a while loop is, remember, a while loop will go on forever until a certain condition is fulfilled. In this case, the condition is while win is not true, everything after the while loop will run forever. So in other words, while no one has won yet, this next set of code will run forever. In other words, we will keep playing rounds until someone wins. So in lots of programs, a while loop will be necessary because it's impossible to know exactly how many seconds or how many statements like the user will go through. Depending on who's using the program, the amount of times they'll do something can vary. But so a while loop means you can essentially end it at any point as long as that condition is fulfilled. In this case, the condition is winning, but for another program, it might be, say, after they finish like writing down a form or something else that requires user input in the program. And we have some extra print lines in order to tell the user what to do, which is always a good idea. And then finally, you get next piece of input, which is going to be the player choice of what column they picked in this, which is going to be a number between 0 and 6. Because remember, since our board is going to have 7 spaces, then each space is numbered from 0 to 6 in the code. You could, for example, change this to 1 to 7 to make it seem more logical, like seem more natural. But whenever you actually use the number you get from the user, you will have to subtract 1 from it in order for the program to actually use it correctly. Because the program right now only has a list from 0 to 6. That's how it forms it. So if you do want to change it to 1 and 7, which will make it like more natural to most like humans, since we usually start counting from 1, you will have to, for example, add a -1 here. So because that to the computer, it always starts counting at 0, not 1. So you'll have to essentially move it back 1 to account for it. Right now, we'll just leave it at 0, 6. So then we have this while loop here. This is another example of something that might take a variable amount of time, depending on who's using it. In this case, it's checking to make sure that the user did not enter an invalid input. In this case, invalid input simply means a column that is already filled. Because in Connect 4, and this specific program's purpose, in Connect 4, if a column is filled, you can't place another piece in it. So obviously this is supposed to simply check if that happens. We create a method, a little program essentially, that has its own input, the picked column by the user and the current board that is being used. And this mini program right down here will return a number as stated here. And this number will represent whether or not this number has two possible values. This number will either be a positive value between 0 and 6. Yeah, between 0 and 6, where essentially this number is the row positions it can fit in. And the other possible value is -1, which means it's impossible. Lots of times you'll see a program that returns a number, and oftentimes they'll have a default return value of -1. This is usually because a lot of times you return numbers, you usually work with positive numbers. So if you ever want a way to tell if the number is just bad or invalid, a lot of times you'll just have return a negative number because it's separated from all the positive numbers you're working with. So you know if it's negative, then it's completely valid. So if it returns a -1, it means it's not any possible position, since the program will never recognize a -1 row. It starts from row 0, not row -1. However, and this piece of code is simply to tell us where the piece can go. So essentially what the code is doing here is that it's going to start from the top of the column. Sorry, it's going to start from the bottom of the column and keep working its way up until it either finds an empty space where it can put the piece in, or if there is no empty piece, then it will return -1, saying there is no possible position. So as you can see here, for loops mean repetition. So this allows us to repeat something. In this case, this code is allowing us to repeat the check while at the same time changing our position. So it's checking a new position each time. Remember, a for loop isn't just simply repeating, but always contains a changing value that will cause the code to do something slightly different each time. In this case, the general meat is the same. It's always going to check a position in the board, and it's always going to check if it's equal to 0. But the slight change is that since the actual value it checks will be different, since position is constantly decreasing until it reaches 0, or in other words, the end of a column. And the reason we're starting from the maximum value and going to the smallest value is because of the way that, at least in this way that we're coding it. So most Java and most programming languages really, whenever you create a 2D array with values, something like this, for example, right? In this case, this would be a 2D array with 4 rows and about 10-ish columns, right? The way we read it most of the time is the top row is, this is row 0, this is row 1, this is row 2, and this is row 3. So and connect 4, right? We're checking, we want to put the piece in as low as a row as possible, as long as that row is empty. So we have to check from the biggest number and we have to go up essentially. So in this case, we start from the lowest possible place. In this case, it would be row 3. And then we keep subtracting 1 from the row position. So it goes to 2 and then to 1 to 0. And then it checks if any of those positions is equal to 0, which in this case would mean empty. Our board stores numbers, remember, and the only possible numbers, and the only numbers we want to use is 0, 1, 2. 0 represents an empty space. 1 would represent, like we said above, red or player 1, and 2 represent player 2 or black, like we said above. And if it ever finds an empty space, then we know this has to be the lowest possible position because we started from the lowest possible position and only return. And as soon as there's an empty space, we would immediately return that value. For loops are very commonly used to check lists because it's a very easy way to go through each value systematically without missing one, without like accidentally missing one or doing something different. This will allow you to check every single value with the same criteria. If you, of course, in some situations, you might want to check every position of the list differently, but in that case, you would have to be more specific then. But if you just want to check each individual element with like a specific criteria, for loops are usually the best way to do it. So after we've confirmed that, we can then change that spot to the player numbers, changing it from a 0 and empty space to something that we actually, to the stored value of the current player. which right now is 1 since we haven't finished the term. Then the program will move on to the printing section. Essentially, this is our first major output, which is essentially just printing out the board. So like I said earlier, for loops are very useful when going through lists and we want a specific operation to be done on each part of a list or graph. In this case, in our board, we want to print out each element, and we want to print out each element depending on what number it is, what value it has, and so the user can understand it. In this case, we store the value to make it easier to hold on to, and this value is going to be at row and column. And remember, so if you put, you can stack for loops together in order to accomplish something. In this case, we stack a for loop here that has a stored value of row, which is equal to 0, and it will increase with each repetition. This one has a stored value, which is called column, and will increase with each repetition. And because this for loop is inside the other for loop, this means that this for loop will run first, it will finish running, and then we'll move on to the second for loop with the second repetition. In other words, we start here with row is equal to 0. Then we move on to this for loop where column, and then we start with column equals 0. And every time we get to this end, we get to the end of the for loop, which means we have to go back and increase column, but row's value is still 0 because we have only reached the end of the first for loop. We haven't reached the end of this for loop. And you only ever change values of a for loop. You only ever check if you ended or not at the end. And since we haven't reached the end of this for loop, then row will not change until this for loop finishes. And this for loop will finish once column is equal to board and equal to this number. Because if it's equal to, then this condition is no longer true because it's not smaller, it's equal to. And then when that finishes, then this row will increase by 1 and then repeat this again. This allows us to systematically go through every single element in any 2D array. And this will also work for any grid array. Like if you wanted to make a 3D array where you store a list inside of a list inside of a list, you would simply do the same thing, but you have to add an extra for loop inside. This will allow us to check every single value in a 2D array without repeating any and without any repetition, without any wasted space. And the specific operations can repeat each time is simply checking the value. If this value at this space is equal to 1, then we print out a red space. If it's 2, we print out a black space. And if it's not equal to anything, if it's not either of these two values, the only other value is 0. So it has to be an empty space. And then finally, we print out a line so that we move on to the next line. So this way we will print out a row and then we'll move on to the next row instead of putting them all next to each other. Then we have some final operations to go through in which we check for wins and we check for ties. These two is probably the hardest part to code in Connect 4 because everything else is simple operation. You check if it's full, you check, you print out the entire list. But this too is the parts that's really unique to Connect 4, which is I'm gonna sell. And finally, here's where you alternate the rounds between player 1 and player 2. If the current player is 1, we switch it to 2, and otherwise we switch it to 1. And since this happens at the end, that means when we repeat, it will go on to the next player. Now, so today, I want you guys to think about, how do you think we would have to check wins? How do you think we would have to check our storage? And how do you think we would check it for a certain criteria? We know in Connect 4, the certain criteria is 4 in a row. If you have 4 of the same color in the same row, then that would give you a win. So how do you think we would start checking the wins in a program then? How do you think we would go through our board and see if there's a 4 in a row? How would you start thinking about it? Well, we can start, like Son said, we can start by thinking about the way we did tic-tac-toe, and we can also we're taking tic-tac-toe where we checked for 3 in a rows, and it's kind of similar here. While it is kind of similar in that instead of checking for 3, you check for 4, it's not that simple because in tic-tac-toe, the size of the board is always 3 by 3. So all you had to do was just go from the end of the list to the other end, from the one end of the list to the other end of the list. Since the size of the list is always 3 and the number of places you have to check is 3, then you don't have to think much more. But because a Connect 4 board is usually larger than that, where if you have where if you want to check if you have a 4 in a row, right? It might have spaces to the left and right or above it, then that complicates things a bit. So if you remember in tic-tac-toe, the way we checked wins, we simply iterated, we simply repeated, we simply checked each space in a row and then each space in a column. If every single one of those spaces in a row and column matched, we return true. Otherwise, then this method had to return false. In Connect 4, it's slightly different. The first bit of the check win is generally the same. We have 2 for loops in order to iterate through each row and column. And like in tic-tac-toe, we each double for loop checks one specific pair. In this case, this for loop specifically is only checking vertical wins. This piece is specifically meant for vertical wins. We have 2 for loops and then using these 2 for loops, we're going to check it. However, notice I put -4 here. Essentially, the reason is instead of going from all the way from the top row to the bottom row, we can recognize the fact that we don't actually need to check the last 4 rows because we've already checked them. Does anyone have an idea why? This little piece of tree. It's a little bit like a kind of little trick way. You don't have to check every single row. While you could, for example, start from like the first row and then count down. So 1, 2, 3, 4, and then count down from the second row, 1, 2, 3, 4. When you get to the last 4 rows, you don't have to check the third to last row, second to last row, and first to last row, because any vertical win from the last couple of rows will have already been counted for in the previous couple of rows. There we go. So like this example here, right? If we want to check vertical wins, we would start at some row and some column and constantly decrease the row we're looking at. So you start from row 0, and we look at row 1, then 2, and then 3. And then if all 3 of these values have the same number, then we return true. And then we would check the next row. We start from row 1 instead in the same column number and go down again. And when we reach row 3, we would count row 3, row 4, row 5, and then row 6. However, when we go to row 4, we don't have to check row 4, row 5, or 6, because row 4, the only possible vertical form rows it can contain would be 4, 5, 6, and 3. But we already counted that when we checked 3. And meanwhile, the other one, 5, 4, 3, 2, we already checked that when we checked 2. And the other one, 4, 3, 2, 1, again, we already checked that when we checked 1. The same is true for any form row that starts at 5 or contains 5, contains 6. By starting from top one, going down 4, starting from the second one, going down 4, starting from the next one, going down 4, so on and so forth, this allows us to check every single possible vertical combination. And allows us to not have to check the last 3 rows. And this is what the -4 is here for. We don't have to check those because by doing this strategy, we already checked those, so to speak. And then, so as you can see here, we did a for loop. This is a third for loop because remember, the top 2 for loops merely find the starting element. It will get each element, but the second for loop is meant to check the 4 elements after that. So this 2 for loops will find an element, and then this third for loop will then repeat 4 times, each time moving the element we're checking down 4. And then that for loop will finish, and then it'll move on to the next element at the top, and then it'll check and then it will use the third for loop to check down 4 times again. So you see there's a triple for loop here. And that also means that this will generally run a lot of times. Does that make sense? we can, yeah, and then also, and then we simply check. And then in order to check if it's a 4 in a row, rather than have remembering each space, all you have to do is check whether or not one of the spaces does not equal the current player number. If it ever does not equal it, then we know there's not possible for a win to be a spot. But if we check each of the 4 elements, and this is never true, each spot is always equal to player, then we know there has to be win there. So that allows us to return true. Essentially, instead of knowing each 4 elements does equal player, all I have to do is know that at least one element does not equal. And as soon as we see that, we can store that single value as a false and then check it at the end of the for loop. We can then repeat this process for checking horizontal wins. And so essentially we can essentially reuse and recopy this code with some slight justifications just for that. In this case, now the column we're checking has a -4 because instead of not having to check the bottom 4 rows, we don't have to check the last 4 columns. We then repeat this process of checking each where we get an element, check the 3 elements next to it, including itself, and then we check whether or not they will equal or don't equal player, and then return true or false based on that assessment. Diagonal wins, however, are a bit different. Diagonal wins require an incorporation of both the horizontal and vertical wins, which I talked about earlier. Since a diagonal usually involves a line that is moving horizontally and vertically at the same time. As you can see here, this means that first off, we don't have to check the last 4 rows and last 4 columns, because go back to our example. If we start any point, it will go down. It'll go down 4 and left 4, meaning that any point that is within the 4x4 square we made there, that was created from going down 4 or right 4, we don't have to check those if it's at the end of the list, since you can't go past further. And if you went backwards, it would already be checked. And this is specifically for top left to bottom right wins. And then instead of just changing one position like we did here, we have to change both positions, because again, in this case, it's both the X and Y positions are moving simultaneously. So we have to move both of them. And finally, for the other wave diagonals, you can do very similar, but because it's going backwards on one of the directions, you would have to code it a bit differently. In this case, the way I did it is by having row start from, in this case, instead of subtracting 4 from the length, I added 4 to its starting position, because this specific, because the other diagonal, so going from top up, bottom right, going from top right to bottom left, it checks backwards essentially. So we have to, instead of not having to check the last 4, we don't have to check the first 4, because we're starting from because it's going backwards, it actually includes the end for these diagonals would be the left side of the board. And it includes most of the same check. So we would take each position, move backwards 4, move up 4. And if all those 4 values are still within the player number, then we can return true, otherwise false. And finally, for check tie, it's exactly the same from tic-tac-toe. You simply move through every space and check if there's a tie or not. However, notice that here I wrote else if instead of just a simple if condition checking it. This is because specifically check tie doesn't check for wins. It only checks for ties. It's possible for a board to be completely filled, but there's still to be a win. So specifically in this case, check win and check tie are mutually exclusive. Thus, if one is true, the other is not, which is what if and else if, that's what the if and else if statements are for. If this is true, run this, but if it's not true, and only in that situation will we check and then run this. If this is ever true, then this piece of code will not run because it's connected to the else. Or in other words, if this is true, then we run this. If this is not true, else we will run this if this operation is true. If these were not mutually exclusive, then you would, instead of having to write else here, you would write a separate if statement, which will allow both of these statements to run if both of their conditions were true. But in this specific scenario, these are exclusive and thus cannot be combined together. Yeah, so that's how you would write a type code program. But of course, that's not, you don't just want to write it, you always want to test it out to make sure you didn't miss anything. So first we start with the input, say 1 round. Then our next input will be picking columns. So let's say 0. So here you see we can the list, and we can easily check where that is and check our inputs and see if it's doing the way we wanted it to. So specifically in this case, it's printing out each column, each row, and it printed our object at the bottom instead of the top or any other position, which is good. So we know that's working right. We can double check to make sure by putting another piece in the same column and seeing that it does in fact fill up the spot above. So if you remember, so do you remember where in the program does it, well, what method did I use to allow the program to know how to stack the pieces onto each other? You know, like where or how I, do you still remember where or how I did it? Oh, did it cut out? Yeah. So do you still remember where and how in the code that I managed to make these pieces stack onto each other? And you know where we managed to alleviate, do you know where we managed to make that happen? And so remember, specifically, the place we checked it is almost immediately after we got their input with the method check column, and the way we handled that is by when we take a where, and this method takes in an input column, input board, and it has to be a type number and a type of 2D array. And in order to make sure that not only is this a valid column, but that it can also find the correct position, the way we did it is we take the board and we started from the end of the board, or in other words, the bottom of the column, and constantly moved up by going from row 10 all the way to up to row 0. And then if it's ever 0, we know this is the first empty spot because it has already checked all the spots before, and this condition is never true. It won't ever skip because as soon as it returns an output, this program ends because these methods automatically end after it returns an output. So it won't return multiple outputs. It will only return one. The first one never meets. And if it doesn't, if this entire loop for goes through and it never reaches this return and never reaches a valid output, it will return -1, which symbolizes an invalid output. And since this returns an int value, we can use the int value to figure out where in the list we should put it. We know it has to be in the position picked column because that's the column user picked, but the specific position in that column or the row is determined by this method. It's either -1, which as I said before, is essentially means is not possible, since you can't place an object in a negative position in a list. There is no -1 position in a list. And that allows us to know when the user entered an invalid column. However, if it's any other number, we know for a fact that it's a possible value because this for loop is contained inside the list size, so it will only have a valid number. It's only between 0 and the size of the list. So we know that any value it does return has to be valid, and it is also the correct position. which then allows us to then place it there. And specifically in this program, it's not actually dropping the piece. Rather, when the user picks a column, the way we're doing it is we're going actually from the bottom to the top and then checking for an empty space, rather than going down and then checking for an empty space and then putting it the one above. And the way the program handles putting things in a list is that the virtual list obviously does not experience gravity, and it just picks a spot and puts it there rather than having to move it down. Then after the board is then finished, and after the board is finished, it then prints out the board, as you can just see down here. And the way it prints out, in order to print out the board, we use a double for loop in order to read through every element. Because obviously, if you want to show output, especially like a whole list, you don't want to miss any part of the list. And in order to actually print out the list, again, we simply use print statements here. It either prints out red, blue, or empty. And we can vary this output. We can change the output based using if statements, which rely on a true false condition. And specifically, because there are else's in here, this makes each if statement exclusive, where if one of them is valid, none of the other ones are valid, even if the condition is fulfilled. Usually here, if value is 1, then this will true. Otherwise, it will output this. And if value is 2 and otherwise, we'll print out that. This all statement, because there's no possible way for value equal to 1 and 2. And even if it did, it shouldn't matter because the one spot should only have one value anyway. Then this empty statement here, instead of, it's meant to print out essentially an enter button, where after you print out the entire row, you want to move on to print out the next row. You don't want to print the rows next to each other. And this statement right here, print line, tells the program, okay, essentially, we're moving on to the next line now. The major difference is print does not have an ln next to it. There's no ln. And ln simply means after you finish printing this line, move on to the next. And since this space is empty, this statement is saying after you finish printing out nothing, move on to the next line. And then finally, like I said before, our final operations here will check the input of the board with the new input of the player. Since by this point, the board has already changed based on the player input. So then it will check based on that, and then of this updated board, depending, and then as we already went through before, it'll go through each position and then deliver a bit different output based on the possible outcomes. Yeah, like I said before, the main parts, the most important part of the program is the operation. So you handle changing an input to a valid output. Actually getting inputs and outputs is fairly easy. All you have to do is either say use a scanner to gather in keyboard input and simply use system input lines to deliver output. The main difficulty in programs is specifically getting that input to become that output, or in this case, getting each of the picked columns to eventually transform into a board and a win or lose or tie statement. All right. So does anyone have any questions about Connect 4? All right. So let's move on a bit. So I want to try introducing graphics and classes today. Essentially, this looks cool and all, but what if we could make it colorful and have extra stuff on it? Essentially, now we're going to make the program and the outputs look much prettier rather than text. Right now, all we've been doing is having our output vary based on text, but now we're actually going to try drawing stuff as well as learning what makes Java an object-oriented programming. I know I hyped up the drawing a bit, but we're going to start with classes a bit first. So as I talked about in the very beginning, how Java is object-oriented, where it's focused around creating objects and programming around these objects. Specifically, that manifests in classes, which is essentially, and a class is simply a way to create an object. Scanners are objects, as well as arrays and strings are all objects. What that simply means, an object is simply a piece of code that contains a way to store various inputs as well as various methods to transform the input. Specifically, so in other words, a scanner is essentially a pre-made class. The way the scanner class we're using is a pre-made object. It's a pre-made class that allows that instead of having to gather a user input thing every time, the scanner object, it's a pre-written class that already has all that necessary input. So now we're going to learn how to create them. The base template for a current class is simply the word class. The name of the class, let's say, I'm just going to call it first class. And so a scanner class, for example, would probably actually, yeah, we're going to use the scanner class, for example, has int variables in containers that essentially as containers to store what the next int the user inputs in, string containers called the user's next word input. And it also contains methods like the next int we've been using so much. And also contains methods that look something like this, that essentially returns the next int or next that we've been using. So whenever we call a scanner, like up here, what we're essentially doing is we're creating a new copy of this class. I'm creating a new copy of this class. And then every time we call in this class, we called whatever you put the name as, which I usually put as SC. And in order to get input, we call the various methods attached to it, like next int or next. And the way the program handles that is it goes to SC, sees, oh, it's a type, it's a variable that holds a scanner object. So it goes to the scanner object's code and it finds, okay, so the user typed next int, the program types next int. So it goes to the next int method and returns and processes the next int, which in this case is simply just returning a number. Yeah, so that's part of what basically we already know. Objects contain stuff to store things in order to actually do things with most of the time. They also contain methods, which essentially allow you to manipulate the items, the data inside a object or class without having to actually have the data. And this is in the case of scanner, the methods allow us to essentially get the data that the scanner holds about the user input. But the new thing about classes is that they have constructors where essentially a constructor just details what happens when you first create a class. And that's public. Constructor is simply the word public because if you want to create a thing, and all constructors are generally public, because if it's not public, that means only the class itself can access its own constructor, which means nothing else can make the class, which makes the class useless because the class is not meant to be used by itself. It's like you see with scanner, it's meant to be used as part of a program. So it has to be public. In other words, any program is able to access it. And it's in a similar form to a method. It can take in inputs that you plug in, and inside it, it'll do things like, for example, specifically the way a scanner might be constructed. So you can see scanner, we usually put system.in in it, right? We usually put a system.in in it here. And the way the constructor might work is, so this system.in would be the input for a scanner class. So it would look something like, so it looks like that, where system.in is essentially just a way to read inputs. It's where the input is stored, and a scanner will take that as an input, and then you store it somehow, or usually by, say, usually by storing it in an outside variable like that. So it will take in the user input, whatever you want to read in input from, usually system.in. It will put it inside its own storage space, so it won't forget it. And then when you actually call like the next in stuff, it'll go to that input storage string reader and then read numbers from it. And of course, the scanners are not the only version of object, but this is essentially one way to view it. Essentially, classes are ways to store lots of code. For example, one use of classes is to organize things together. For example, you could have a class named person, and inside a person class, for example, inside a person object, you could, for example, store data such as their age and like their name. And then for the constructor, whenever you create a person, you would have to enter their name and their age, and the person would then store it, and then I would have various methods, like for example, return name or return age, which would allow you to get the age and name of the store person. And maybe it might also have another method called, say, increase age, or have a birthday party where it increases the age by 1, or change name, which would allow you to change the name, and various other guys. Essentially, classes are ways to store extra bits of code and keep them organized and separate without having it be one giant 500-line document. And by organizing like in this, it allows it to stay much neater. You can look at a class, see, okay, it's all a person class that stores information about a person. You could also have a class, say, named student, which could be really similar, which could also be similar to person, where it also stores age names, but also stores, say, IDs. In fact, if you wanted to be clever, you could create a class named student that extends person, where right. And essentially, there you go. And essentially what what extends does is simply it takes the extended class, in this case person, essentially copies the items in person into student. So you can see here that student is also has a constructor named age and does something with it. And what this essentially does is student also has a variable called name and age that it takes from the person class. So if we create a student, essentially it has all the public attributes and methods of a person class plus a personal ones. However, a person class cannot access the student stuff, but a student that extends person, since students are also a subset of people, can access stuff from person and its own stuff. Essentially, classes are sort of like methods, and that they're also sort of mini programs as well, except they're more like mini files since they store much more. Yeah. All right. Did I go too fast? Is it fine? Any questions about classes? Yeah, that was a bit quick. Because we don't have. I want to see if we get to the drawing stuff because we only have a few minutes left. Yeah. So essentially, a quick refreshers that classes are essentially ways to organize code. Technically, you don't like ever need to use them, but like basically everyone does, and it's the difference between writing a giant essay and writing an essay with like chapter titles and stuff. It's way more fluent, way organizes code, and also if you don't, even if you might not use it, everyone else around you is going to be using it to organize things. So like don't be lazy. And the way classes work is that essentially you might notice that this is also class, but this one has this type of constructor called main. Essentially, what this does, it tells us the program, it tells the program this is the actual main part of the program. This is the thing you run. Meanwhile, these classes down here do not have the public static void main. And that tells the program these classes are essentially objects that are not going to be run. You can call them in a main program and do stuff with them, but by themselves, the classes will not actually run by themselves. And so in order to actually use classes, you have to do essentially what we've already done with scanner. Remember, scanner itself is already a class. If you want to use the person class we created earlier, you simply have to you would create a person object. We can label it, and we can give it a name person, which is equal to and this set of code is saying we create a bucket called person, which holds a person object. And this bucket will contain a new object that we just made that is a person, which has a name, and it needs a name and age in order to first create it. And then like scanner, you can then call its methods with which like I wrote an exit method down there, or you can also access its public variables, like the age of it in this specific circumstance. Essentially allows you to store data much more fluently and easily. If you didn't create a person class, you'd have to store all the ages and names separately together. And you have to, every time you wanted to find one, you have to like iterate through each element looking for the one that matches. But by creating a person object, you can simply just go through each person to find the relevant one rather than going through a giant list. Yeah, and then finally, the other important thing to talk about is extensions, where if you can create a class that extends another class, and we call it a subclass. Essentially, they have a parent-child relationship where the child inherits things from their parents. Specifically, they inherit the containers, the variables. They will inherit the methods, the public methods of the parent, and they will also inherit the constructors. Essentially, they copy most of the stuff from a basic class and put themselves. So you can see here. As you can see here, I can call the nextInt method. I can still use nextInt, even though the student class does not have a nextInt, because it extends a person, or other words, it becomes the child of the person class and thus copies its nextInt method. Extensions allow you to make essentially subclasses. Like if you made a class called car, you could make a class called Toyota that extends car. But because not all cars are Toyotas, the Toyota class can have unique elements to it that other cars don't have. And another important thing is that while multiple classes can extend a single class, like in this person example, you can create a class student, which extends or inherits items from person. You also create a class teacher that also extends person and takes the element and copies the elements of person. But one class cannot extend two things. So if you had, like I said before, a class teacher, the teacher cannot extend student and person because the language is simply not built to having to handle two different constructors and everything. Essentially, it would create way too much trouble. And usually, essentially, it can only ever go down. You can't have essentially one child, each parent can have multiple childs, but each children can only have one parent. Is like probably the best way of thinking about it. You can't have, okay, you can have, in real life you have two parents, but specifically in this case, you only have one. But each parent can have multiple children. So we're about to reach the end here, which actually took long. Yeah. So for next class, what we're going to do is we're going to talk about graphics and paint. And if you want to get started on that, you can look at resources like Oracle's, but essentially the main things we're going to focus on is Java panels and Java frames, as well as the paint method, which will allow us to actually create images, like actual, colored images of stuff, rather than simply text images. Like this is fun, but next class we're going to focus on actually how to create actual images and how to and we've been focusing on keyboard input. We're also going to do actual mouse input next time. All right, but there's not enough, I don't have enough time to talk about anything else. So if you have any questions, you can stay back. But otherwise, that's the end of this class.
Thank you.
You're welcome.